Alright guys, you made it. This is the last day of notes for this first chapter. We're going to talk about absolute value. Absolute value basically represents a distance from 0 on the number line. And the thing about absolute value is it is always positive. Okay, so when you take the absolute value of a number, you get a positive answer. Should never get a negative answer. So, you should always get, you generally can get two answers, because what's happening here is, in order to get 22 for an answer, this number in here, when it's all said and done, can be 22. Or couldn't you also get a negative 22 inside the absolute values and then the absolute value turns it to 22? You can. So there are usually two answers for absolute value equations. So remember that. If you're doing absolute value on the test and you get one answer, chances are you maybe did it wrong, unless it's a 0 or a no solution. So let's do this. This middle piece here can be either 22, or technically this middle piece in here can equal negative 22, because if it does, the absolute value will then turn it to a positive anyway. So you end up solving for two different equations. So let's do this now. We get 5m is equal to 15, or we get 5m is equal to negative 29. Our final answer is m is equal to 3 and m is equal to negative 29 fifths. Now if I ask for, let's say I want these answers just up here in the set of real numbers. If I ever give you this set notation, I want answers in that notation. So this is not acceptable yet. You need to say the answers are 3, because it is a real number, and negative 29 fifths. And we talked about that earlier, I think in sections 1.3. Okay, so that would be your two answers that solve that inequality. Before you do that for number 2 though, you cannot just say, okay, let's set all this equal to 8 and negative 8. You need to isolate. So isolate the absolute value symbol, which means get it by itself. So first thing you do, move the 16 over. We get 4. Absolute value of 3m plus 1 can equal to negative 8. And if you divide that by 4, you get the absolute value of 3m plus 1 is equal to negative 2. And now you have to look at this and go, can I ever get a negative 2 from this? Because what do absolute value symbols do? They always make something positive. Okay, just look at that and go, there's no way that anything I put in here for an m will give me a negative 2, because these symbols will always make it positive. So this is a case where you do no solution, or you can give me the symbol for no solution. Now if you went ahead and solved this and said this equals negative 2 or this equals 2, you would get some points off, because technically that's not correct. You would get extraneous solutions. Alright, and finally I want you to solve this one over real numbers. And again, you can try it yourself first, but I'm going to just, pause it if you want to do that. We're isolating the absolute value, so this turns into a negative 2 absolute value of 9 minus x, and then we get a negative 10 plus 4 is negative 6. Divide by negative 2, and you get a positive 3. Now this is acceptable because we can get a 3, anything positive out of here. Now we have to look at what makes the inside either 3 or negative 3. So that means 9 minus x can equal 3 inside, or 9 minus x can equal negative 3. We move over the 9. 3 minus 9 is negative 6. We move the 9 over. Negative 3 minus 9 is negative 12. Divide both by negative 1. X can be 6. X can be 12, and if I gave it to you in set notation, you would say it is 6, or 6 or 12. And those are your two answers. Okay, that is regular inequalities. Now we're going to do absolute value inequalities. Here are the rules for this. Think of this: less than, great, or. And this is only when the absolute value is on the left side. So when absolute value on the left. Less than, greater. Okay? So we look at this symbol here, And that tells you kind of what kind of absolute value graph you're going to have when you graph this. But in order to do these, it's very similar to what you did up there. But you also have to switch the inequality. So break apart and switch symbol for the negative one. And what that means is I look at this problem here. First of all, just write down what the problem is without the absolute values, because we know that 23 minus 2x can be less than 17. Now this is a less than symbol, so this is going to be an and graph. So I'm going to just write and here. Now the other one is the middle can also be a negative 17. So we're going to say 23 minus 2x can be a negative 17. Now here's what happens. Because we changed it, the symbol flips here too. So our second inequality is flipped. So this is what happens when you have an absolute value inequality. Write the first one out as is, decide if it's an and or based on less than or greater, and then break write it again and flip the symbol and make the other number negative. And then just solve them. This is now back to the last lesson we did. Move the 23 over, and when you move the 23 over, you get a negative 6. And then you have to divide, and when you do that, make sure you flip the symbol. You get x equals 3. And, or I'm going to use the and symbol, we get negative 2x is greater than negative 40. When we divide by negative 2, we flip the symbol. Negative 40 divided by negative 2 is 20. So this is what I have, and now I have to graph it. And again, it's an overlap one because of how it's set up, and you should see that when you graph it. Here's the graph. I have my 0, my 3, my 20. X is bigger than 3, but it's not equal to, so it's going that way. X is less than 20. So there it is, going this way. And is an overlap. So where does it overlap? It overlaps here, but not really, because there's nothing filled in there. There's nothing filled in here, but everything in between here is an overlap. So that means that this is the actual graph for our inequality. And this is our answer. Okay, so again, less than, greater. So let's look at this next one now. We can't say less than or greater yet. Well, yeah, you can, because get it isolated first, just like before. So we have our absolute value of 4x plus 5 is greater than or equal to 7. Now, I just said it's greater than or equal to, which means we're doing an OR graph here. Now we break it apart. Write down 4x plus 5 is greater than 7 or equal to 7. Or we're going to have 4x plus 5 can be less than or equal to negative 7. Again, the second one, you just flip the inequality symbol and change it to negative. And that'll give you the other side. Alright, now we just solve them. 4x is greater than or equal to 2. Or we have 4x is less than or equal to negative 12. X is greater than or equal to 1/2. Or x is less than or equal to negative 3. There's my answers. If I graph it, it looks something like this. I have 0, negative 3, and 1/2. And now I'm going to fill in the bubbles. X is bigger than or equal to 1/2. So it looks like this. X is less than or equal to negative 3. Looks like this. So in OR graph, you take each piece. Remember, you take everything. So we have this piece for our final answer and this piece for our final answer. So this is my final graph. I have each piece. We're not looking for overlap there. And that's our final answer for absolute value inequality with an OR. Again, greater, look at the symbol right here. That makes it an OR. This less than makes it an AND. Alright, now we have two different models we're going to learn about tolerance, because in the real world, when you're manufacturing stuff, there's an acceptable amount of wiggle room. Everything's not going to be the exact same size. There's always imperfections in machinery and anything else that gets produced. So for this case here, a manufacturer has a 6 ounce or 0.6 ounce tolerance for a bottle of salad dressing, advertises 16 ounces. So right away, you guys should be able to think about, okay, if it has a 16-ounce bottle and it has a 0.6 ounce tolerance, that means that it can go either way. 0.6 ounces for the answer. So it could have 16.6 ounces or 15.4. Well, we actually have a model for that, and we will be giving you this model. Actual is the value that we want. We don't know what it is. We'll call that x is our actual. That's usually your variable. Minus the ideal. The ideal is what's given usually to you, and the tolerance is also given. So this problem actually is pretty easy. We set it up. We have the absolute value of x minus our ideal would be 16, and then it's going to be less than or equal to the tolerance. The tolerance is 0.6. And that's the model right there. Write and solve. We didn't solve it yet though. So here's the model, but you can double check by solving. This just goes back to what we did the last problem. It's less than, it's an and graph. So we have x minus 16 is less than or equal to 0.6, and we also have x minus 16 is greater than or equal to negative 0.6. That's how we would solve this. You get x is less than or equal to, add 6 over, or 16 over, and you get 16.6. And x is greater than or equal to, if you add 16 to a negative 0.6, you get your 15.4. So logically thinking, we got these numbers ahead of time. But now this absolute value inequality gives us the numbers we wanted. Okay, so we solved it. It did not say to graph it, so I am good with this. Okay, so that makes sense. It has to be less than or equal to 16.6 or greater than or equal to 15.4. That one is nice because it just gives you the numbers. There's also another tolerance model where we have to do a little bit more work, and it's called we have to deal with the extremes. So a city ordinance states that pools must be enhanced by a fence that is from 3 feet to 6 feet high. That probably should say enclosed. So, but now that I look at that, write an absolute value inequality describing fences that do not meet this ordinance. Okay, so we want to know do not. So this is saying it does meet it. So if it's do not, we're probably going to have to flip this symbol at the end, but let's see what happens. The height of the fence is our actual. That's our variable. Average of the extremes. The extremes are 3 and 6 feet. So to average them together, hopefully you guys remember, add the two numbers, divide by the number of numbers we're adding, which is 2 here. So 9 divided by 2 is 4.5. So now I have the average of the extremes. Now, the tolerance is equal to, we don't know what the tolerance is though. What is the tolerance? Well, if the average of the extremes is 4.5, our tolerance would be equal to the average, which is 4.5, minus the lower bound. Because it can be either, you go from 4.5 to 6 or 4.5 to 3. So either way, it actually doesn't matter which way you do it, but this will give you a positive number. So our tolerance for this problem is 1.5. It is not 3 or 6. So now we have 4.5 and 1.5. So our inequality becomes the absolute value of h, which is our actual, minus the average of our extremes, is, again, it does not meet. Notice how that's in yellow over here. We want it to be greater than 1.5, because the tolerance model is oh no, the tolerance model already is taking that into account. But if you're not sure which way the inequality symbol should go, you can write it out and then solve it. So for instance, I wrote my model just to double check that this is the correct model. I'm going to solve it. I have h minus 4.5 can be greater than 1.5, or I have h minus 4.5 less than negative 1.5. And if I solve this, we get h is greater than 6 or h is less than 3. So this was correct because it asked what does not meet the ordinance. Well, the ordinance says it has to be between 3 and 6. This is saying h is bigger than 6 or h is less than 3. So this inequality is correct. It shows us the values that do not meet the ordinance. Okay? If you have questions on that, we will talk about it on the next day, and we'll go and practice a couple more of these problems.